Thank you for joining me for today's webinar. I'm going to get started in about 5 minutes, so sit tight and I'll be right back. All right, let's get started. Hello and welcome to today's webinar. Thank you so much for joining me. A few notes before we get started. Audio is provided via the GoToWebinar app over the internet, so please enable your speaker. The application has muted your microphone. There is a questions tool in the app, which you can use at any time to ask me questions. So please feel free to do that. Today I'm going to talk about integration of automation lifecycles. So we're going to talk about the benefit of integrating the different automation lifecycles. By that I mean functional safety, cybersecurity, and alarm management into a streamlined work process. But first I'm going to introduce myself. My name is Kate Hildenbrandt. I am a product manager here at exida. I'm responsible for the strategy, roadmap, and feature definition for our exSilentia software. I'm also focused on providing training and software support for our customers. So if you have any questions, my email address is right here, khildenbrandt@exida.com. Please feel free to email me directly with any questions you might have about this webinar, about our tools, anything. So I have a short overview of exida. So exida helps customers achieve safe and reliable solutions through 3 different pillars of our company. One of those is our lifecycle services. So anything you have to do for functional safety, cybersecurity, alarm management, we also offer these services. So you can have an exida professional help you to achieve these tasks. We also have enterprise tools that will help you to do them yourself. So anything in the functional safety lifecycle, any of those lifecycle tasks, as well as cybersecurity and alarm management can be done with one of our tools. And then we have certification and assessment that will help you achieve compliance. So we believe that these 3 different groups together can help you with your overall safety approach and help you to optimize your process when it comes to safety. We do have worldwide locations, as you can see on this map. I personally am located right outside of Philadelphia, but hopefully you see another exida location somewhere near you. So let's start with an introduction of what I'm talking about with integrated automation life cycles. We know that to get an overall idea of the risk in your system, you have to consider potential process hazards as well as cyber attacks. Now we do this hopefully using the guidelines given to us by the international standards. So each of these guidelines, we have one for functional safety, cybersecurity, and alarm management, and they create a detailed guideline to analyze, design, and implement safeguards against risk and cyber threats. They also help us with a guideline to operate and maintain. However, they're often carried out by totally different groups, and there's very little interaction between them at times. And so there is a need there for a better work process. Let's dive into some details on this safety life cycles as they are. Functional safety life cycle is defined by IEC 61511. This is probably very familiar to you. I do have it organized here. You see the analysis phase in yellow, the design phase in red, and the operation and maintenance phase in gray. This is usually owned by engineering or process safety, and of course it includes analysis, design, and maintenance of safeguards to protect against hazard scenarios. We also have an alarm management lifecycle, which is defined by ISA 18.2. And as you can see, this also has an analysis phase, a design phase, and an operation and maintenance phase. But this scope includes identification and rationalization of alarms. Design and implementation of these alarms are followed by operation, maintenance, monitoring, and management of change of a master alarm database. And then we have the cybersecurity lifecycle. So this is defined by IEC 62443. It's usually owned by operations technology and information technology. And again, the scope includes assessment of a facility for inherent risk, subsequent design and implementation of countermeasures to protect against cyber attacks. But as you can see, there are similarities here as well. We have an assess phase, which is much like the analysis phase in the others, an implementation phase, much like design, and a maintain phase. And so you're already seeing some of the overlap or synergies between the different life cycles. So we know that cyber attacks not only impact business from a financial perspective, but they can also cause the same process hazards that we are worried about in functional safety. So we know it's no longer adequate for plant operators, engineers, to only be aware of process hazards and risk. There's a few hurdles, however, to having everybody aware of process hazards and cyber attacks, and that is the difference in vocabulary and the work process are providing hurdles for effective communication between OT and engineering. But we really can't escape it at this point. The functional safety standard IEC 61511 now emphasizes the need for a cyber assessment. They want a security risk assessment, including description of threats, the likelihood and potential consequences of a security event, the determination of requirements for additional risk reduction, etc. And it emphasizes the responsibility of the owner operating company of the facility to take care of this. Additionally, it outlines the need for your SIS design to provide necessary resilience against security risks. So at this point, your functional safety standard is already calling out the need for you to have a pretty good idea of what the cyber threats are and to implement countermeasures against them. So the idea here is to use best practices from the different life cycles to create an efficient work process that not only drives consistency and is efficient, but promotes communication between the different groups involved. And so here you see sort of a summary life cycle where you have your assessment, design, and operate and maintain phase. And the idea here is you can use similar methods for some of these different phases. This would give you a complete plant and enterprise view, so you'd have an idea of all the risk that is inherent in your system that could affect the operation of your process. So to get a better idea of where these overlaps are, we have a graphic. And here you can see the alarm management lifecycle, the functional safety lifecycle, and the cybersecurity lifecycle, and all the different places where they overlap. So listed on the side, you can see the first is hazard identification. You're going to want to take your process or your zone and conduit diagram, break them into smaller pieces, and see what could go wrong. In some cases, your safeguards for functional safety or your countermeasures for cybersecurity are alarms. And so that ties into the alarm rationalization process. You need to document your basis for why you need the alarm. And then you have to keep in mind if that alarm is used as a countermeasure or an IPL in the analysis phase for functional safety or cybersecurity. You then use that hazard data to determine your design criteria for both your safety instrumented system and your cybersecurity countermeasures. And so this comes in the form of your SIL verification and your SL verification for your design of the safeguards and countermeasures. Finally, you need an event response while your plan is running. You need to know what your operator is expected to do if they have a process hazard, if they have an alarm, if they have a cyber threat that occurs or a cyber event. And so all of these are tied together in that event response. And finally, in all cases, you need certification of devices and personnel. So you need to know that the equipment you're using for your application makes sense and that the people doing these jobs are the right people for the job. So this is a lot of information in one graphic. What we're going to do is take a deeper dive into these areas of overlap. Let's start with professional certification. So obviously, with any job you do, but especially when it comes to safety, you want to make sure that your personnel are capable of performing the work that is in front of them. So you want your personnel to have an appropriate level of training for the duties they have to perform. You want witness of suitable performance by another competent person, auditable records of training and qualification, and in some cases, external accreditation by a recognized professional body. Those of you attending our webinar are probably aware that exida is a recognized professional body for professional certification. So if you're a functional safety professional, you can become a certified functional safety expert or a certified functional safety professional. For cybersecurity professionals, you can become a CACE. And then you also want to have your devices certified. So devices, elements, and systems should be certified by an accredited independent third party. So for functional safety, compliance to IEC 61508 is evaluated, including review of your development process, your product testing, and your SIL capability. And obviously, that's your safety integrity level. For cybersecurity, compliance to IEC 62443 is evaluated, including review of the development process, the product testing, and your SL capability. This is your security level. Again, exida is ANSI accredited to perform these certifications as well. Let's dive into some of the other overlap areas between the life cycles. We're going to start with hazard identification. And here I have pointed out the functional safety analysis phase for the functional safety life cycle and the cybersecurity analysis phase. These are pretty similar. So you have your hazard and risk assessment. This involves taking your system and breaking it into smaller parts to analyze the inherent risk. For functional safety, you're going to start with your P&ID. For cybersecurity, you're going to start with your zone and conduit diagram. And then once you've figured out the inherent risk in the system, you're going to define safeguards for safety or countermeasures for cybersecurity against that risk. In many cases, that is going to include alarms plus operator intervention. Once you've defined your safeguards and countermeasures, and you've completed your analysis, in both cases, a safety requirement specification is required. So this document is meant to communicate the design criteria to your design team. And this will include requirements such as your target SIL for safety or your target SL for cybersecurity. So what's this look like for functional safety? Well, you start with your P&ID, as I said, and you're breaking it up into smaller parts called units and nodes. Any deviation to your process, any challenge to your process is called a deviation. And you need to document what is the cause of that deviation and what is the consequence. This is going to determine your risk. Once you've figured out what the risk is, you can determine if you need safeguards, and you can define what those safeguards are. For functional safety, it's often alarms plus operator intervention, pressure relief devices, or perhaps a safety instrumented function. Well, what does this look like? Here's an example of a process hazard analysis, or what we might call a HAZOP, in exSilentia. And here it's showing in this sample problem, we have a chemical batch reactor, and we have a high pressure scenario. The deviation is high pressure. We document how this could happen. That is the cause. We document the consequence of it happening. We have a safety consequence and a business consequence. In both cases, the risk is pretty high, so we document the safeguards that are inherent in the process against it. And so these safeguards include a high pressure alarm, a high pressure alarm. We have a instrumented protective function and a rupture disk. We also document here a recommendation. And so this is your basic HAZOP. This is what it would look like in exSilentia. The cyber risk assessment isn't so different. In this case, instead of a P&ID, you're taking your zone and conduit diagram. Your system is divided into smaller parts called zones and cyber nodes. Any challenge to your system is called a threat. So you want to document the cause and consequence of that threat. That determines your risk. If your risk is high enough, again, you're going to implement countermeasures. In this case, a countermeasure could be an alarm with operator intervention. It could be a firewall switch with access controls. And in some cases, it could even be something like security screening of employees. But the process to analyze your zone and conduit diagram is very similar. So this is what it would look like in exSilentia CyberFacts. And again, we have your threats. In this case, we have hardware. You have your causes, your consequences, Again, we have a safety and a business consequence. And the frequency plus the severity are determining your risk. In this case, the severity is your security level. And then once you've figured out if the risk needs risk reduction, you can implement countermeasures against it. In some cases, those countermeasures, again, are going to be alarms. So here we have listed a fault alarm for a switch monitoring Ethernet access. In this case, an alarm would basically be telling you that the equipment is no longer working. This might be a high-risk scenario where you want the operator to be involved in replacement of that switch, or it might be an IT issue. But in both cases, you're using the HAZOP methodology. You're taking your system, breaking it into smaller pieces, and documenting it much the same way. So you're using your best practices from functional safety to help you with your cyber risk assessment to make sure that you have the countermeasures you need in place. And again, this ties into alarm rationalization because some of our safeguards and countermeasures were alarms. So let's jump into the alarm rationalization process. Again, I have the entire life cycle for alarm rationalization here. And you can see the yellow analysis phase, the red design phase, and the gray O&M phase. What I want to focus on here is the identification rationalization. So first you have to identify potential alarms or candidate alarms. Well, we've done that in the functional safety and cyber in the process hazard analysis and the cyber risk assessment. Not only is the need for the alarm documented, but the risk, if it doesn't exist, the cause and consequence to a hazard scenario is all documented. It's important to have this documentation for the rationalization, but it's also important for the rationalization to know if you've used that safeguard or countermeasure as an IPL and taking credit for it. In the rationalization phase, you determine which alarms are necessary. So that's a big part of that. You're going to establish design settings, and you're going to document your basis in a master alarm database. Then you can move on to the detailed design. What does this look like? Well, we have a tool called SILAlarm, which is another exSilentia. And here you can see the rationalization of safety and cyber alarms here. I want to emphasize the master alarm database design basis includes the cause, the consequence, the corrective action, and time to respond of the alarm. So by cross-referencing the alarm rationalization with the safety and cyber analysis, you're improving traceability and clearly communicating the design criteria. So in my screenshots, you can see that for LAH 202, this alarm, you're documenting the LOPA that it's associated with and the HAZOP that it's associated with. You're checking that it is a safeguard and an IPL. You're giving it a probability of failure and a risk reduction factor. All of this comes from the analysis phase for functional safety or cybersecurity. For classification, it's saying that this is an independent protection layer class because it knows that this is included in the LOPA. And so it's important to have this cross-reference. It's important for the different teams to be communicating so that you don't make any mistakes. You don't exclude an alarm that really needs to be included, or vice versa. So that's where alarm rationalization comes in there. Then you need your hazard data in both cases for safety and cyber to help with your design. So here I'm highlighting the design phases for functional safety and cybersecurity. And in both cases, you use frequency-based targeting to determine your design criteria. So for functional safety, you determine the target SIL level in your LOPA and SIL selection. Then you determine the achieved SIL level through SIL verification. It's not so different for cybersecurity. There you determine the target SL level during the cyber risk assessment. Then you determine the achieved SL level through SL verification. So you can see the similarities here. Let's take a look at what that looks like for functional safety. So here we're jumping into the LOPA. And you might recognize in this sample problem that you have an initiating event, which was the same as your cause in the PHA. Likewise, you have your IPLs, which were your safeguards in the PHA. So you're seeing your high pressure alarm, your high pressure alarm, your SIF and your rupture disk. In this case, we're determining the risk reduction factor needed for the SIF by making sure your target frequency matches your actual frequency. And so this is where the frequency-based targeting comes in. So for this SIF, the target risk reduction factor is 100, and the target safety integrity level is then SIL 2. So this is determining your design criteria. Then you achieve your design criteria through SIL verification. So this is our silver tool, and in it, you're modeling your SIF, you're choosing your equipment, you're choosing your proof test intervals, your proof test coverage, etc. And this is going to calculate for you your achieved safety integrity level, among other parameters that are pretty important, mean time to fail spurious, etc. But that is how you determine your achieved SIL level for functional safety. It's pretty similar for cybersecurity. In this case, again, you're looking at SIL verification, but it looks a lot like the LOPAX sheet, doesn't it? So in this case, your hazard data is being used to achieve your SIL level. So again, your target SIL is determined as your severity in your cyber risk assessment. Here, that information, again, the initiating event is your causes in your cyber risk assessment, and your IPLs are your countermeasures from your cyber risk assessment. And in this case, you achieve your SIL level by closing that gap between the target frequency and the actual frequency. And so for each countermeasure, you're given a certain amount of credit, and the SIL is achieved when actual frequency meets target frequency. So you can see the overlap here and how you're using best practices for one to achieve the other, and how some of the language, though slightly different, could help you understand, help bridge that gap of communication between one group and another. So that's design. We're going to get into implementation and then operation and maintenance next. So implementation and testing. You need to do your factory acceptance tests and your site acceptance tests to properly implement your safety instrumented system, your countermeasures, and your alarms. So your factory acceptance test is done prior to installation in the field. And this includes verification that your application program for your SIF logic solver and your alarms are implemented correctly. It also includes verification that your countermeasures for cybersecurity are implemented correctly. The site acceptance test is performed after field installation. And so this is including verification that all parts of the SIF are installed and functional, all countermeasures are installed and functional, that your alarm trigger and notification in the HMI is working, and that you have means for successful operator response. So you can't just have an alarm. You need the operator to be able to respond. And so the FATs and the SATs are touching all three of these components. And so, again, synergies between these would obviously make it a more efficient process. What about the O&M phase? Here we're bringing in all three: functional safety, cybersecurity, and alarm management. These phases of the life cycle in each case look very similar. All three include monitoring during operation. So you're always going to have to monitor the performance of your safety instrumented system, of your countermeasures, and of your alarms. You need an event response plan in all cases. You need to do routine maintenance and testing, as well as periodic assessment, and you need to have a potential for modification. So let's say if you are monitoring your operation and you realize that your safety instrumented system or your countermeasures are not adequate, you're going to have to go through a review. You're going to have to change it, maybe go to the start of the life cycle again, or maybe do a management of change kind of modification. But in all cases, to demonstrate compliance with the standards, you have to collect that data during the life of your plant, and you have to compare it to your conceptual design. So that is another large area of overlap. Not to mention, what about what the operator has to focus on? So during operation of the plant, he needs to focus on, number one, keeping the plant online. So you want to increase uptime. You want to make sure that your plant is running correctly. He has to worry about physical security. So who's coming in, who's going out, is anything going on physically. And then, of course, the process hazards and cyber hazards. So for functional safety, you might have process demands. You need to do proof testing. You need to keep track of device failures and respond to them, repair, replace. For cyber hazards, you need to keep track of your cyber alarms and your active and passive diagnostics. So if this is all on the operator's plate, then the people handing him tasks need to understand what his load is, what he's dealing with. And so that is another area of overlap. So by communicating on functional safety, cybersecurity, and alarm management, you are creating a more efficient work process. Hopefully it's saving you time, and it's giving you a high-level look at all the risk that is inherent in your plant. And so again, here are the areas of overlap. But the main message here is that integration is key. So these areas present opportunity to streamline your work process and improve communication. There's some specific project and operational benefits. So again, awareness of all potential hazards and required risk reduction is very important. That's a good project benefit. You don't want to analyze one area and realize that you missed the other area. By increasing efficiency, you're increasing your project velocity. And by taking less time to do these tasks, by using best practices as an advantage, you're reducing your project cost and project schedule. During operation of the plant, this should increase availability. If you're aware of all your risk and you have a good event response, then it's going to be quicker if there is some sort of event to get back online. Hopefully, the idea is that you have enough safeguards or countermeasures that you're not going to have an event at all. But if you do, you have a comprehensive event response plan and, again, reduced operation and maintenance costs. Hopefully you're spending less time and money on cyber threats, process hazards, and events. And so that is the benefit of an integrated life cycle. And that's it for today. So I don't have any questions, but if anybody thinks of anything on this topic or another topic, please feel free to email me. Again, my email is khildenbrandt@exida.com. I do want to emphasize that people should send in any ideas that they have for our webinars in 2018. We love to hear what you feel would benefit you by hearing from us. And otherwise, have a happy holiday. I hope everybody has some vacation time and yeah, take care. Thank you.